My name is Usman Nasir, and she already introduced very well. And first of all, I would like to thank Dr. Marco for inviting me and giving me a chance to speak to you people. And today I'm here to talk about the power converter topologies with the medium frequency or a high frequency link, isolation for grid integration systems. I'm working with Professor Pat, who delivered the lecture yesterday. And also I'm working with Dr. Alessandro Costa-Weber. And we are working with the PMC group, which is at Nottingham University. So I will just like to show the group and the Google Maps. So the Google Maps, the Google Maps recognizes our group. So we have the icon for the PMC group now. And one of the interesting things that I would like to show, we have the Wollaton Park. Wollaton Park here. So this park is famous for this hall. And why it's famous is because the Dark Knight 2 movie was filmed here. So this is the very interesting thing that I have in my slide. So I would like to now move to the content. And so first we have the introduction that what can be the possible topologies that we have in the medium frequency or high frequency link. Then we will give a background of the topologies that already exist and also a new solution which is in the evolution of the new topology. Since we are dealing with a new topology, so we need modulation and commutation techniques for the new topology. We will discuss the scalar modulation, which is the Venturini modulation. Those of you who are familiar with the matrix converters, they will be very well knowing the Venturini modulation and the four-step commutation as well. Since we are dealing with the transformers and the transformer saturation is a big issue in the transformer. So we will discuss how to control the saturation and also a pulse switching cycle feed-forward compensation. And then we will conclude the discussion with the comments on the topology. So we move forward. This is a brief introduction of the future smart grid or future electrical network in which we have different renewable energy sources such as solar, wind, or energy storage systems, EES. So in this kind of network, you can see the power converter is required in each of the convergence stages whenever we are going from one stage to another stage. So each of them has some requirements from the power converter. For instance, if we are dealing with energy storage systems, we need to have the bidirectional power flow capability because when we are charging the battery, the power flow direction will be on the one side, and when we are discharging it, so the direction will reverse. So we need to have the bidirectional power flow capability. There are the requirements, bidirectional power flow capability from the future power converter, and we have need to have the galvanic isolation as well. Because if the fault occurs in such a big system, we want to isolate the fault at the one location instead of spreading the fault all over the network. And we need a modular and a flexible structure because we have different levels of voltage required for each of the renewable energy sources or distributed energy sources. So we need a modular and flexible structure, and also compact in size is another important parameter for the requirement from the power converter. So these are some of the solutions. I would like to highlight the importance of the galvanic isolation in the power converters. So this is one way of providing a galvanic isolation in the power converter. So we have the AC grid power converter and the line frequency transformer and the AC grid. So in this kind of converter, we use the AC grid line frequency transformer, which is operating at 50 or 60 hertz. So the size is quite bulky and heavy, and it's expensive. So it's not a viable solution for the converter topologies. Then what we can do, we can increase the operating frequency of the transformer, and the size will decrease. So what we do, we place the transformer inside the two power converters. So the transformer is now working at a medium or a high frequency range. So we will only discuss this kind of topologies because they have the more cheaper solution, and also they are not bulky in size and they are not heavy in size. Quick introduction about the previous solutions. The first one is the AC to DC and the DC to DC via medium frequency link, which is also known as a dual active bridge, and then we go back to the AC. So in this kind of solution, you can see that we have the 4 H bridges, and each of the H bridges have the switches which are bidirectional with respect to current, but unidirectional with respect to voltage. So we have 3 stages. You can see the first stage, second stage, third stage, and then we go back to the AC. So in order to see the topology, how it looks like, it is this kind of topology in which we have the dual active bridge inside this topology. So another one is that we have the AC to DC and DC to AC, the medium frequency link. So in this one, we have reduced the number of stages to 2. So this is the first stage, and this is the second stage. So in this one, we have 3 H bridges, and 2 of them are based on the switches which are bidirectional with respect to current, but unidirectional with respect to voltage. And since we are dealing with AC of this bridge on both sides, so we need to have the switch which is bidirectional with respect to current as well as voltage. So in order to have a look of the topology, we have the 2 H bridges, these, and the third H bridges, which is bidirectional switches. And in literature, it has been named as a cycloconverter based module. And another possible solution that has been suggested is that we go from AC to AC via medium frequency link directly. So in this one, we have just one converter stage. And in order to have a look at how it looks like, we have the bidirectional switches, which we usually use in the matrix converters. So these bidirectional switches are bidirectional with respect to current as voltage. So we can go from AC to a high frequency AC and then go back to the low frequency AC. So in order for the convenience of reference, we use the name dual CBM. We have the input cycloconverter based module for this part, and the output cycloconverter based module to refer to this part. So the whole topology known as dual cycloconverter based module. So just to give a quick comparison between the 3 solutions, the first one has a larger number of stages, and then we have decreased the number of stages to 1 in the last one. And you can see the converter cell size in the first one is quite big because of the DC link capacitors. And in the last one, we will be having the smaller size because of there is no DC link. So the commutation and modulation will be difficult in the last solution because it is completely based on the bidirectional switches. So we need to commutate it every time we need to move from one state to another state. Another important issue that the converter cell size as well as weight will be much lesser. So that will be a compact solution. So much more lesser weight than the first one or the second one. And but this comes at the expense of the higher conduction losses because the switches, bidirectional switches, they have the diodes and they turn on whenever we need to turn on the switch. The modulation for this kind of topology can be done in this way. We have the AC at the low frequency at the input, and we have the high frequency voltage at the transformer, which looks like this, and then we can go back to the low frequency AC. So in this one, how to generate this kind of voltage in the transformer. So if we turn on the shown switches, we will end up having the positive voltage at the transformer. You can see it's a positive voltage. So when we turn on the opposite switches, we can have the negative voltage at the transformer. So you can see the output voltage remains positive. So in this way, we can modulate this converter. Since this is a medium frequency transformer, so frequency is higher here, and frequency is low here, and the output is low here. So this is the case when we have the demanded frequency, which is equal to the input frequency. This demanded frequency is equal to the input frequency. What happens when we change the input frequency and the output frequency? So in this kind of thing, converter cell, when interconnecting 2 systems, first at the input frequency of, let's say, 60 hertz, and the second, let's say, it's 50 hertz. So the presence of the low order harmonics. So this is a problem with the single cell that we discussed. You can see there are low order harmonics. Since the low order harmonics will be difficult to remove, and we need expensive passive filters to remove them. So this is not a good solution for the systems connecting, let's say, 60 hertz grid with a 50 hertz grid. It works fine for the 50 hertz grid, but it doesn't work fine for the other solutions. So we move to this topology in which we use the dual CBM, 3 dual CBMs, and you can see that we have the 3-phase input, and we have a single-phase output. So in this one, you can notice that we have the cascaded connection at the output of the bridges. So this is a new 3-phase to AC, 1-phase isolated AC to AC topology using the 3 dual CBMs. So this new topology solves the problem of the harmonic spectrum that we discussed here. So this is much better in harmonic spectrum because it has high frequency harmonics which can be removed later. So this is a modularity is still there because we have the same module repeated over the times. And we have the galvanic isolation in the transformers as well, and bidirectional power flow capability as well. So we can think about a 3-phase to 3-phase system which will look like this. We have the 3-phase input and a 3-phase output, which is this is a load to represent a load as a big inductor. So we have a 3-phase to 3-phase system, a new 3-phase to 3-phase isolated topology. So moving next, since we know that we are dealing with switches which are bidirectional and they are same that we use in the matrix converters. So the modulation techniques should be developed in accordance with the matrix converters. So this is a modulation technique we use for the matrix converter, and this is a third harmonic injection technique in which we introduce the third harmonics of the input and the output in the output voltage. So this is the modulation index, and for instance, this is a traditional direct matrix converter in which if we need to get the phase A at the output phase A, we turn on this switch. So this is similar to making this configuration and the pattern of the switches. So in this one, you can see that we have the switches. These are turned on. So we are getting phase A at the output, and we are not getting phase B or phase C at the output. So they are shorted through a shorter path. We are just getting phase A. Is similar to having this kind of configuration in matrix converters. So with this kind of thing, we can get a harmonic spectrum which looks like this. So you can see there are no low order harmonics, so they will not be difficult to remove. The higher order harmonics can easily be removed. So we have these harmonics two appearing at the third harmonics because we introduced the third harmonic injection scheme. So, but they will be cancelled out in the line-to-line voltage. So we can cancel out these harmonics in the line-to-line voltage. So this is a better solution than using a single cell, and it's a new topology. So we move to the voltage regulation ratio. Yeah, so the voltage regulation ratio is the ratio between the output voltage and the input voltage. So we get 86% of the voltage regulation ratio in this one. So this is the waveforms, how they look like, just to give you an idea that this is the input 3-phase voltage and the input current. And this is the transformer voltage that I showed before. And this is the line-to-line voltage, and this is similar to the matrix converter that we have in the matrix converter. So let's move to another new thing that we discovered is like if we have this kind of pattern of switches in this one, if we see we are getting phase A here, and we are getting minus of phase B, and we are getting minus of phase C. Since they are cascaded at the output side, so these all three will add up to make 2A, because if it is a balanced system, so we get 2A at the output. So in this kind, so this shows that we get a voltage regulation ratio that is double from the previous one. So previously it was 86% or 0.86. So now it's 1.73 or 173%. So it's a good topology in the terms that we have a lot of options to play with the switches and make different combinations. So therefore, twice increase in the voltage regulation ratio from 0.86 to 1.73. So since we need to commutate between the states, so we need to define what are our steady states. So this is the steady state 1, and this is another steady state. But this is a 0 state since we don't apply any voltage at the output, so this is a 0 state. And then this is a negative state, you can say, and is an active state as well, and the state 3. So how we move between the states is called commutation. So what is the 4-step commutation? Since we are dealing with a matrix converter type topology, so 4-step commutation technique is quite famous in the matrix converter. So we have two kinds of commutation strategies. One is the output current based, and the other is the input current, input voltage based. So what can be the way that how we commutate using the output current based? So in the step one, if we have the switches which are turned on in the red one, then if the current direction is as shown, we can move to the next state and we can turn off the switches which were not conducting. So there is always a current path in this one. Then we go to the next one and we turn on this switch, and this switch does not short circuit the voltage source. And then we move to the turning off of this switch, because this switch can conduct the same current as that switch. So there is always a path of this current. So then we move to turning on of the other two switches. Then the converter reaches its steady state. So this is just for giving you idea how it can be done in this kind of topology. So we moved from steady state 1 to the steady state 2, and we can also go from other states which I explained, the steady state 3 or steady state 1, and we can move between the states. So what can be the preferable commutation strategy? This was the previous one I explained, is the output current based. So if we see what can be the appropriate commutation strategy, since we have the two bridges, so we can see the input voltage and the input current of this bridge is something like this, and the output current of this bridge is this, and the output voltage is this. Since you can see from here that input voltage is having less high frequency fluctuation, so we can select it as input voltage based commutation at ICBM, and then we can have the output current based commutation at this bridge, since the output current is in low frequency. So we can measure the output current in a way that it doesn't have any error, because if we are measuring this voltage has high frequency fluctuations. So the voltage sensor may give us a wrong value. So we are looking for something which is more not having the fluctuations in the current. So the output current based here and input voltage based here. The saturation of a transformer is one of the most important thing that we need to consider. And why the saturation of transformer occurs is because we have the undesired DC components in the voltage, transformer voltage or current, that can cause the core of the transformer to saturate. So the DC components can occur due to, one reason can be the difference between the turn on time of the switch, and the other reason can be the gate driver delays. So therefore an active control of the volt second of the transformer is required. So a control loop has been considered to introduce the concept, and this is the transformer voltage. We give the transformer voltage to a averaging block, and then we find the average of the DC component over the period of time, which is the voltage period. And then we compare it with something, because since we want the DC component to be 0, so this should be 0, and we compare it and we pass through a regulator, and then we give it to a gain and saturation block. So why we need the gain and saturation block is because we are dealing with small times. So we need to saturate, we need to have a limit of the time so that we can manipulate the time for the volt second balance. In order to test the loop, I delayed one of the switch by an exaggerated amount of time of 0.2 milliseconds, although it doesn't happen, but just to check the loop. So in this one, we can see the red one is the closed loop that we proposed here. So the black one is the closed loop, so it goes back to the 0. This is the error I plotted, so the error goes back to 0. But in the open loop, it doesn't go back to 0. So this will saturate the transformer, and overloop can prevent from the saturation of the transformer. So another interesting thing that can we do with this kind of modulation is that since we can see this is the transformer voltage, and if we zoom the view, we can see that we have some average over per switching cycle. So this area A1 is not equal to area A2. So what we can do, we can develop a feed-forward compensation to limit the flux variations per switching cycle. So these flux variations can help us to reduce the core size, and as well as we can reduce the losses as well. So the saturation control that I explained before was acting on the fundamental period of the voltage. but this will act on the switching per switching cycle. That's the sampling time of at the transformer. So if we try to find out what is the average over the first period, then we can use this formula to calculate the average. And since we were switching before at fixed time, that is Ts by 2, so we can find that there is a 7.74% of the input voltage amplitude, which is quite a big average over per switching cycle. So what we can do, we can change the time where we flip the bridges. Now the new time is T dash. So how we do it, we find the area A1 through this equation and area A2 from this equation, and then we equate those two areas so that we find the time T, which makes the area to balance. So a generalized equation can be found in this way, where n is the nth switching cycle. So if you want to calculate for the first switching cycle, you need to have the n is equals to 1. So we put n is equals to 1 to calculate what is the time we need to switch. So another important thing that we need to mention, that this time is not affecting the modulation strategy, because whenever we move from the state 1 to state 2 that I explained earlier, that doesn't change any, that doesn't have any effect on the output voltage. So in conclusion, I would like to conclude there is a potential in this topology that and more need to be explored by developing some other strategies and modulation techniques. And we also identify the problem with the single cell. So we modify the topology, but this modification comes at the cost of an increased number of switches. So the modularity is still intact. So we applied the matrix converter modulation and commutation techniques for this topology, and we also developed the voltage-based saturation control. But in more practically, we will implement the current control because it's not necessary that the voltage is 0 and the current can also have some DC component. So we implement it through the current control instead of the voltage. So a per switching cycle control that is acting on each switching cycle, making the average over the switching cycle 0, can help to reduce the core size as well as the losses, because the lesser the core size, we will have the lesser losses. So this new topology will have a wider range of applications, grid applications, as well as AC drives. So that's all from my side. If you have any questions, you can ask.